Our next section here, A5, the Okay, if we look here, we have here 1, 2, 3, 4 paces to the right. That's going to the east. Then we're going to go 3 paces north. And this shows you how to add vectors. In fact, if you were to go 4 paces to the east, you would end up here. And then if you went 3 paces north, you'd end up there. So it would be like going from here at some angle up to there. And since this is 4 this way, and since this is 3 that way, and that's a right angle, we can use the Pythagorean theorem to find the hypotenuse of the right triangle. And the hypotenuse would be given by, you would take, first of all, 4 times 4, and you would add 3 times 3, and you would take the square root. So that would be the square root of 16 plus 9, which is the square root of 25, which is 5. So this would be 5 paces at this angle. And that angle, by the way, if you take the tangent of that angle, you get the rise over the run, which we talked about already. This is the slope. So the tangent of the angle is the slope. This is the rise over the run. So if you do that, in other words, here the angle is equal to the arc tangent of 3/4, you're going to get 37 degrees. You might remember that triangle from like in high school. It's like a popular triangle. Notice that when you have a vector, if you move it parallel, so you don't like rotate it, you keep the same direction. If I were to have three paces going north, that vector there is the same as this vector here, because I got 3, and I'm pointing north, So you can move it over as long as you don't rotate it and change the direction, or you can't stretch it or like squeeze it down, because then you would change the magnitude. So this brings us to the concept of the baby vectors. Before we do that, though, let me just show you that this vector here, if I call that r, like if that's the origin, say that's like some radius going away from the origin, we put a little arrow on there to represent the vector. So that r with the little arrow on the top means this vector. Now, baby vectors are little vectors that are in the direction, say east and say north. If I take one pace to the east or one pace up, then we use a little upside down V called a hat, like pull a hat. That's I. We use I and we use J for Y, and then we use K for Z. Here's a better example. Here's my room, master bedroom, where you're looking at here a little I, the little I vector, and this one here going this way is a J vector, and this one going up is a K vector, correspond to X, Y, and Z, the 3 dimensions of a room. So when we do that, in fact, we can make a nice little diagram. It's always good to draw figures in physics. So let's say we have here the x-axis going this way, and we have here the y-axis going that way, and the z-axis going up. Then if I draw a vector to some point, say P, you can call that point there O for origin, and this is the vector, like that. All the points in the room are defined by a point that has X, Y, and Z. Now watch this trick. Now this is 3-dimensional, kind of like perspective we want to do here. If we drop this down, and what we're going to do here is go like parallel. Let's say we go parallel to here like that, and say go parallel like that. Then what this is saying is you're going this way. This is your Y. This is your Y value. This here is an X value because it's parallel to the X-axis, and this is a height, a Z value. Now you can think of going from O to P as 3 vectors. What you would do at first is you would start here and go along the X-axis like this. So that would take X steps along the X-axis. Remember, I hat is a baby step. So that would be like a little unit vector that points this way. Then you would go this way, which would be Y steps along the J. So just think of that little j as a little cute little vector, which is 1 unit in length. And I have to have y of those to get here. And then I would go up here. I would go up here, z, k. So this vector here would be z times k hat. And those three vectors added together would give me r. In other words, x I hat plus y j hat plus z k hat. That would be this vector r. Consists of three vectors, this way, along the x direction, the y direction, and a z direction. So you could, at that origin, O, make three cute little vectors. Say this is along the x-axis, this is along the y, and this is along the z. You know, three cute little vectors. Each of these have length 1. And then if you want to actually make like 6 steps, it would be 6, x would be 6, then you would have 6i to get here. Maybe this is 8 j hat. The steps, the j hat means you gotta be going to the right. And then the k hat means you gotta be going up. Here's a picture from the book, but I always encourage you to sketch your own pictures. It's very, very important. So that's showing the three baby vectors, the unit vectors, and showing the point, say P in the room, and the vector that goes from the origin to point P is this red vector. Okay, that takes care of vectors, and then the last thing would be the tensor. So if we go here to 3, the tensor, here's the idea. We have a board that we can define its orientation by having a little vector come out of the board, like perpendicular to the board. And then we're going to apply a force at that point there. Now, if we apply a force at that point, the force vector would have a force component along the x direction, a force component along the y direction, and a force along the z. In other words, the force vector has 3 vectors. Just like here, this r vector can be thought of as having 3 vectors. The x I hat 1, the y j hat 1, and the z k hat 1. So you got 3 vectors. Now, each of those forces, though, has an ability to like push, in general, has an ability to push the board in or to stretch it to the right or like stretch it down, right? Like shear forces. So in other words, each of these forces has 3 effects on the board. The inward thing to break it, or like to stretch it to break it that way or down. So in that sense, we have 9 components for the stress. So in other words, we're going to use the symbol sigma. And here, you can think of this as, I'll put down a K and an L. This is like the row, and this is the column, right? In fact, you could use R and C if you want. And then what we're going to do is say that XX, like this, XY, and XZ. Now, a lot of times the X is used, they just use a 1, Y they use a 2, and a Z they use a 3. So this could be also 1, 1, 1, 2, 1, 3. So it's basically a component, a stress component of the X component of force operating in the X direction. But in general, because that board can be at all kinds of weird angles, this would be that X component of force operating in the Y direction of that board as the board is changed. And then this is the X component of force operating to do some other kind of a stretch. So I think the simplest way to think about it is that each force, there's 3 of them, has three effects on the board in terms of like pushing it and stretching it one way or the other. And then you can list those like this, where this is the second component of the force affecting 1, 2, 3 dimensions. We're not going to be doing this in our class, so you don't really need to worry about this. I just wanted to show you that we're looking at here something that's more complicated than a vector. You could also write this as like 1, 2, 1, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And there's nothing, particular about this K and L. You could say IJ, and this IJ is not the IJ of the other unit vectors, just an index, So that would be the idea of the tensor. But you could say that this has 9 components, that the vector has 3 components, and the scalar has 1 component. So you could say that if this is the tensor, this is the tensor of rank 2, because there's 2 indices here, see, or indexes. Here the vector has 1 index. You can think of this as sort of an AX, I hat, AY, J hat, AZ, K hat, and some kind of general vector. X is 1, 2, and 3. And so we would say, since there's only 1 index here, 1 subscript. So you have 2 subscripts, rank 2. You got 1 subscript, this is a tensor of rank 1. Here you have no subscripts, just a temperature, like there's no subscript. So that's a tensor of rank 0. So you can consider them all tensors, where the scalar is a tensor of rank 0, the vector is a tensor of rank 1, and the tensor of rank 2 is a stress, as an example, stress tensor. So one last comment. My falling in love with tensors was studying Einstein's general theory of relativity, which is very advanced. We won't be doing that in our class, but just to show you the field equations, here they are. Plus a constant times little g. This is a mu nu, Greek letters, and 8 pi g, capital G. We'll be talking about that. It's a gravitational constant in our course. Speed of light squared, and t mu nu. These things, Greek letters, are used when it can be 0, 1, 2, or 3. And the regular index situation, like a K, would be 1, 2, or 3, or an L. So the Greek letters can have the 3. So here you have 3 space, and you have time. You have 4 dimensions, Einstein. This is geometry over here, and this is matter and energy over there. So you have your space, you have your time, and you have your matter and energy, because Einstein taught us that E energy is mc squared. So you need to consider both in there as a matter. And this is the cosmological constant, which Einstein introduced so that the universe would be static. He didn't want the universe to be doing something like that, so he called that the biggest blunder of his life when we discovered the universe is dynamic. There's an expansion going on. So Einstein said that was that greatest blunder of his life, but it turns out that constant, we believe, is non-zero, and Einstein is even correct when he's wrong to some extent. But the idea there, if you had all these galaxies, like on a sphere, and let go, they would want to come together. That's dynamic. But if you have a little repulsive force over great distances, it would hold them out. But the idea is that the galaxies are expanding, that there was a big bang at the beginning and that they're expanding. So there is a dynamic universe. So you don't really need this fudge factor to stop things. So that cosmological constant, though, is non-zero. So Einstein has an element of truth even when he's wrong. So this is basically saying geometry, space and time, and this is matter. So the matter and energy distort the space and time. A beautiful set of equations, the field equations, with the infamous cosmological constant here. This Greek letter here is a lambda thing. uppercase lambda. And these are tensors, so you have rank 2 because there's 2 indices. Isn't that cool? 3 for space and 1 for time. All right, just a little aside inspiration and personal history there. Okay, we'll see you next time.